Okay, thanks, Dave. Thanks, everyone. I'll just start these videos here to give you a flavor of what I'll be talking about today, which is the coordinated motion of these active filaments on spherical surfaces. And the vast majority of the simulations that I'll be discussing today were performed by a former PhD student, now a postdoc, still in the group, Tim Westwood. So he gets a lion's share of the credit for a lot of what you're going to see. Okay, and so just to kind of get everyone on a level playing field, I'd just first like to talk about, well, the first part of the title, which is a filament. So what do we mean by calling something a filament? And really what I'm thinking about is an object that is slender, so it has a very high aspect ratio, and it's flexible and elastic, so you can bend it. Let's see if I have a filament kicking around. I guess I have my wire here, right, my chart. So it's flexible, so I could bend it. I could also twist our filament, but in terms of I can't stretch it. I'm going to be considering it inextensible. As you might imagine, its shape can be described by a curve in three-dimensional space. And this deformation, being able to bend or twist, can be described by the rotation of a material frame along the curve. So bending, so one of the vectors in our frame is going to be the tangent to our curve. That bending will describe how that changes along the length. And then twisting is described by rotations about the tangent. Okay, all the filaments that we're going to be discussing are considered to be sufficiently small and surrounded by a sufficiently viscous liquid, such that all inertia of both inertia of the filaments and inertia of the fluid can be ignored. So we're in this overdamped limit where the hydrodynamics is described by the Stokes equations. Okay, and then just to contrast between the two different cases of passive and active. So a passive filament is one where we assume that if you deform it and then exert a force on it to cause a deformation and then let go, eventually your filament will return to any kind of rest configuration, whether it be straight or one that's prescribed. And this is, we contrast that with an active filament, which is what we'll be talking about today, where we have some mechanism where internal stresses are generated that lead to self-deformation. Okay, and we'll be talking about the coordinated motion of a bunch of active filaments. And the inspiration and the motivation for this work comes from looking at the collective motion and coordinated motion of cilia and flagella and the tissues of our body and those used by microorganisms for propulsion. So on the left here, you could see a layer of epithelial lung tissue, and you could see the metachronal wave that gets established by these beating cilia that you have. And on the right here, we have a volvox. And if you zoom into the surface of the volvox, you can see all the little flagella of the algae cells on this or on the surface of the volvox. And their coordinated motion, you could see visualized quite well, induces a fluid flow at the scale of the organisms, and of course that's what allows it to swim and move through the fluid. Okay, so and I would say that understanding this fluid motion is really, I guess, one of the problems that I would say kicked off our whole field, going back to the works of Lighthill, which should have two L's, should change that immediately, and Taylor as well, developing things like the swimming sheet and the squirmer model in order to say, well, suppose we knew kind of how the surface was moving, can we say something about the propulsion of the body whose surface is deforming, or in the fluid flow that's generated as a result of that motion. But I would say perhaps maybe a more modern problem is thinking about, well, what's kind of coordination needs to arise in order to generate this effective surface motion. And so one of the workhorses of answering this type of question is what I would call maybe a reduced model, where you take can everyone see my cursor, by the way? Dave?
Yep.
Okay, excellent. Yeah. So where we replace one of our beading filaments with a bead that moves along a, I guess, nearly, or in some cases, circular path. And so that's, you can see this kind of illustrated here with an image from an experiment of flagellum, and the kind of model that they use to represent its motion along this, or the bead's motion along this prescribed path. And in its most primitive form, this model would entail having this bead move along a circular path with some force that, I guess, in isolation would allow this thing to move at a constant angular velocity around the circle. And then you can start throwing in Stokes slit interactions with neighboring beads moving around a circular path and examine how they organize. And I think one of the nice things about this type of modeling is that it really draws a connection between looking at how these, or I guess the phase of these rotors characterized by this angle, I guess phi in this case, how the phase difference between neighboring rotors evolves with time, really draws the, can build on the literature of coupled oscillators and things like the Kuramoto model and the Adler's equation to describe this kind of dynamics. And it has been quite successful in illustrating things like metachronal waves, and it's also been flexible enough to include things like flexibility and changes in the this kind of circular path that you might want to prescribe. Okay. Right. Okay. But building up from that, these types of models, at the same time, there's been a lot of consideration of actually resolving the filaments and their dynamics and seeing how filaments themselves can coordinate. And I would say one of the key things about using these types of models that comes up, at least has come up in my mind quite a bit in simulating these systems, is how to drive the motion. You need to make a choice about how do you actuate and move your filaments around. So in these two cases, what we have are, well, in the top case, we have filaments that are driven at their base. So they're attached to a rigid surface, they're driven at their base. And what you allow for is that when the angle of the tangent with respect to, I guess, the normal reaches a certain value, you can change the direction of this torque. So you have a geometric switch that couples the motion of the filament with how it's driven. And similarly, at the study below, they use a similar kind of switch where you allow for the filament to reach a certain curvature, at which point it can change its motion. Okay, so you allow for this coupling or a feedback mechanism between the geometry that it achieves and how it's driven internally. And when you do this, you could get things like metachronal waves at the scale when you have, say, a 40 by 40 array of filaments. Or if you're just looking at pairwise interactions, you can exhibit things like bistability of, say, an anti-phase or in-phase undulations. Okay, but one of the things that we'd like to incorporate also into our models is looking at what happens when you have them have our filaments or our model cilia distributed along various kinds of surfaces that you might encounter. For example, a spherical surface, as we saw in the case of Volvox. And there's been some nice studies recently showing what can happen, or perhaps what becomes important when you consider, say, the motion of the individual filaments. Okay, so this was a nice study recently, I guess, kind of in two papers, I would say, in JFM and PNAS, looking at what happens when you don't allow for the dynamics. So you're prescribing the kinematics of all the filaments, but really, how does this type of model where you're actually considering the individual filaments, even though their motion is prescribed, how does that differ from what you would normally have when thinking about, let's say, a squirmer model? And I think one of the main things that comes out of this really is that a lot of the, if you're thinking about energetics, a lot of the dissipation is occurring in, is related to the motion of the cilia themselves, right? So thinking about hydrodynamic efficiency and the efficiency of propulsion, you're really going to want to be thinking about what's happening in this layer and the filaments in this layer, and how they're, or the energy associated or the cost associated with moving them through the fluid. Okay, and at the same time, you could do things like putting these model cilia rotors instead of on a planar surface, on the surface of a sphere, to try to capture, in this case, the geometric effect of the curvature of the surface. And one of the nice things about this system is that there is a Green's function. It's not the most pleasant of Green's functions to deal with, but there is a Green's function for a no-slip surface or no-slip spherical surface that you can utilize to capture that in the model. And one of the things that you could show is that if, or it has been shown, is that if you allow these rotors to move around in a plane locally parallel to the spherical surface, metachronal waves are linearly unstable, right? So you can get synchronization, but you don't get metachronal waves. But if you instead tip it, so the plane in which your rotor moves around is perpendicular to the local tangent plane to your surface, you can reestablish the metachronal waves. And by having them at an angle, so you set the angle at which they are to, I guess, the meridians, you can generate kind of the swirls that you would observe in Volvox. Okay, so one of the reasons why I'm bringing up a lot of these, I guess, different but related studies is that we kind of, I think, in our simulations and what we have here, I'll just run it, really kind of draw from a few different aspects or a few different, perspectives of the different types of models I just discussed. So for one of the things we want, really we're thinking about driving our filament motion, but we wanted it to be very non-biased, right? So we didn't want our filaments to beat in any particular direction. So so on all the simulations that we're going to discuss, we drove our filament motion by an instability in such a way that there was no preferred beat direction. So I'll discuss that, the details of that in a little bit. And in doing so, we really didn't want to also introduce any kind of preferred orientation relative to the surface, because we really wanted to not only explore the role of the geometry of the underlying surface, but its topology as well. And what I mean by that is, if you think about the position, or I guess the displacement of the filament tip, it really is a vector field. And the vector fields on the surface of a sphere have to have defects in them, or defects or singularities in where they need to go to zero. And so we would like these defects to naturally evolve as part of the coordination, as well as see how they affect the coordination and motion of the filaments. Okay, and the final aspect that we wanted to address is really, if you allow for coordination, how does that allow for the underlying surface to move? And is there a difference between allowing the underlying surface to move or move subject to a force-free and torque-free condition, or holding it fixed? Do you get two different kinds of coordinations depending upon the conditions of the underlying surface? Okay, so these are kind of three things we wanted to address kind of all simultaneously, but they're also related to one another. Okay. Right, so there are a few computational challenges that arise when you start thinking about, okay, I want to simulate a bunch of filaments. In 3 dimensions. So one of them really is having to capture both bending and twisting. So you're going to want a good way of keeping track of this frame that you need to evolve along the length of a filament. The other thing that comes up are these constraints on the kind of filament or positions along the length of each filament and their tangent vectors. So you want to retain this inextensibility as the simulation evolves. Another thing is that this deformation is typically floating in the background. There's a fourth derivative. So you're really going to have to figure out a way to deal with numerical stiffness. And at the same time, if you're at low Reynolds number, all of these things are interacting with each other through long-range hydrodynamic coupling. So you're going to want to build in some kind of, or allow for your computational framework to build in fast solvers to handle that aspect. So one of the, we have a recent publication that addresses each of these. So that's its methods for suspensions of passive and active filaments with, well, I guess, Simon Scholler, Adam Townsend, who's now at assistant professor at University of Durham, Tim Westwood, who's also who's done the simulations for these active filaments on spherical surfaces. So you may want to, I'm going to skip over a lot of the details regarding the methodology. I'll just give a summary. So you wish to look at this paper, but I think the most important thing, if you're interested, is to look at the codes on GitHub. We have a nice simple MATLAB implementation there, so you can really see how the methods work in practice. And what I'm going to discuss now is kind of our solution to these kind of 4 different computational challenges. But there's been a lot of work recently kind of looking at these challenges from slightly different perspectives, either in the context of, say, slender body theory, or maybe imposing the constraints on the velocities of the individual segments that you're dealing with rather than the positions, which is how we do it. So there's a few different perspectives on how to address these challenges, and I'm just going to go through how we do it. Okay, so in our case, we always just start off with the force and moment balances per unit length along the length of each segment. So what we have here are lambda are going to be the force on the cross section of your filament, and m is going to be the internal moment on the cross section of each filament. And how these change as you go along the length of the filament will depend on the forces and torques per unit length exerted on the filament. Okay, so along with the force and moment balance per unit length, we also are going to have a kinematic constraint that that basically the position of the cross section is related to a special vector called t hat, which will which will be, or I should say the derivative of the position is going to be related to this vector, unit vector t hat, which we want to be the tangent to the curve. Okay, and when you write it like this, that you see that the this force on the cross section, lambda, is going to be the Lagrange multiplier that is enforcing this kinematic constraint. Okay, so that leaves us with needing to figure out what these bending moments are, and those will be given by a constitutive law, and that will relate the bending and twisting to how this frame, given by t, mu, and nu, vary as you move along the length of the filament. Okay, and I should say that there we have these kappa mu and kappa nu and gamma naught. These are preferred conditions, so you could set your filament to relax to a non-straight configuration. But in everything I'm going to discuss today, those will all be zero. So all of our filaments will relax to something straight. Okay. But one of the, I guess, the ways we handle keeping track of how this frame varies as you move along the length and in time as well is to use unit quaternions to capture their rotations. Okay. So with that force and moment balance, the first thing we do is discretize and turn it into our force and moment per unit length balances to a force and moment balance for each segment when we discretize. And we discretize also our kinematic constraints for each segment. And in doing so, it's written a bit cryptically, but what you actually have here, splitting the force and our torque into its hydrodynamic and non-hydrodynamic components is really similar to a low Reynolds number mobility problem for a collection of rigid particles. And so this is kind of what you're going to want to solve to get the motion of all of your segments and or I guess your velocities and your angular velocities of all of your segments. Okay, so this is this low Reynolds number mobility problem. So you know that these hydrodynamic forces and torques are going to be linearly related to the velocities and angular velocities of all the segments from all of your filaments. And this matrix that is going to couple them is going to be given by some solution or approximate solution to the Stokes equation, subject to the appropriate boundary conditions on on the surface of your filaments. Okay, or some approximation to the boundary conditions. And so I wrote it in this very general way because when we were thinking about our framework, we were really thinking about developing something that could interface with different levels of approximation or different kinds of hydrodynamic models, depending upon what a user would like. So really, as the framework that we've developed really can, provided that you do have this linear relationship, you can use that model with this framework that we've developed, and we've also wanted to really make it independent of how you perform this matrix vector multiplication, whether you use a matrix-free method, so we've done that with the force coupling method, or if you're evaluating this kind of directly and using a direct matrix vector multiplication or a pairwise evaluation of, say, the RPY tensor, which is what we'll be using today. Okay, so really we think about this as a function in our code, which is give me forces and torques, and it spits out velocities and angular velocities. Typically, this is going to be the most expensive part of your computation. Okay, and so as I had mentioned, what we're going to use for the hydrodynamics for when we present our simulations is going to be this RPY tensor, which is really based on the far field hydrodynamics of spherical particles of radius a. And you could develop it for just relating forces and velocities, or you can have kind of a broader, allow also for torques and rotations of your segments, which is the incarnation that we use. And A is going to be the hydrodynamic radius of our segments. So we could just evaluate this pairwise, and we do so using our GPUs. Okay, and so so we have our force balance. That gives us a low Reynolds number mobility problem. We solve that to get our velocities and our angular velocities, and that allows us to update our positions and our quaternions for each of the segments. And this is the step where we deal with our numerical stiffness and also our constraints, because we actually have a differential algebraic system of equations that we need to treat. So the first thing that we do is apply an implicit time integration scheme, and it's a geometric time integration scheme because it treats in a nice way the Lie group property of the quaternions. So it treats the fact that our quaternions themselves must remain units. That forms a group. And so the geometric aspect of our scheme treats that quite nicely. But when you apply the BDF scheme to the system of equations, what you get in the end is a system of nonlinear equations that we can first treat by substituting the constraints into the updates. So that allows us to satisfy the constraints exactly, at the same time reducing the size of our system. And then with the remaining system of nonlinear equations, we can apply Broyden's method, which is a quasi-Newton method with that starts off with a guess at the Jacobian, and we can form a guess at the Jacobian using a diagonal approximation of our mobility matrix. Okay, so I should say a lot of the work for being able to solve what's going on is really kind of all dumped into how well your Broyden's method works and how that converges. Okay, so let me check the time here. Okay, good. So, right, so as I'd mentioned earlier, what we're going to want to do is drive the motion of our filaments in this way that doesn't bias its motion, right? So there isn't a preferred beating direction or anything like this. And we do this by using a follower force. So what do we mean by that? It's kind of like the low Reynolds number equivalent of like an inverse hose pipe instability, where we prescribe a force at the end of our filament in the direction minus the tangent at the end. So you can imagine having a perfectly, starting off initially with a straight filament and prescribing a force in the minus tangent direction at the end, so it's compressional. And eventually, if you increase the magnitude of this force here, given by the dimensionless parameter little f, your filament will eventually buckle. If it was a buckling problem, the force would remain in the same direction, right? It would bend and gravity would remain in the same direction. But in this case, since the force follows the direction of the tangent at the end, your force will start to push laterally, and you can imagine what happens when that occurs. Okay, so we'll talk about that. So that's one condition at the end, at the free end, and then at the surface. So we're consider some planar surfaces just to see what happens, but also at the spherical surface, we're going to consider a clamped end condition where your tangent is going to be equal to the normal of the surface at that position, and the velocity of the attachment point is equal to the velocity of the surface at that location. Okay. So then what we're going to do is take a bunch of these filaments, distribute them as uniformly as possible on the surface of the sphere. And the sphere itself is going to be made up of a bunch of RPY particles, about 16,500 of them, that we constrain to move as a single rigid body. And 16,500 of them, if you take just the sphere and put a force on it, I think it gives the Stokes drag to say less than 0.1%, something like that. That's the reason why we've resolved it to this level. Right, and so that's going to be a, I guess that will complicate a bit the mobility problem that we were discussing before, but I don't want to go into the technical details of that. But this is how we enforce the no slip condition on the surface. And we consider two different conditions on the sphere. One is where it's held fixed, so we don't allow it to move at all. And another one where we say that the total force, so the force on all of the filaments and the sphere is equal to 0, and the total torque on all of the filaments and the sphere is equal to 0. Okay, so we have these two different conditions that we can impose as well. Okay, so this follower force, it's nice to look at what happens when you have a single filament before going into what happens when you allow them to interact with one another. Okay, so this follower force has been studied quite a bit, both in 2 dimensions as well as 3. And here the bifurcation parameter will be the magnitude of the force that you apply to the end. If the force is very low, nothing happens, right? So you don't get any buckling. But if the force is sufficiently high, you have a bifurcation. And one of the interesting things is that the 3-dimensional motion emerges first. So the first thing that you see happening at first bifurcation that you have is that you start getting a whirling motion. And then if you keep increasing the force, you find that the stable motion is one where it is beating in a plane. And then if you keep increasing, you get some kind of combination of the two where you get beating, but the plane in which it's beating changes with time. Okay. So for the simulations that I'm going to talk about today, we'll be dealing exclusively with this planar beating regime where, or typically our typical force values are going to be this diamond here, F220, and this diamond here, F330. Okay. Okay, so it's nice to look first at what happens in the case of a planar array. So here's a bunch of these on a planar surface. The no slip condition here is resolved by modifying the RPY tensor itself in a similar way that you would use images for just Stokes slit. And so here I think it's, if I remember correctly, just over 1,024 filaments. And initially they're all straight. We give them a little perturbation and then let the system evolve. And this is what we see happening. First, you start getting these patches of synchronization that, and with some boundaries in between them. And eventually these patches kind of start to merge with one another. And you'll see that eventually, perhaps, the whole thing synchronizes. Maybe not in this video, but perhaps in this next one, where you could see it a bit more clearly. We're looking, if you make a vector field of the tip displacements. So here's what happens initially. This is also probably meant to hypnotize you. So initially you could see that there's this coordination here, but you could see that you get these defects that emerge. So here's something that looks like a center that you have so that you get coordination around these defects. And as time goes on, you could see these defects kind of begin to disappear. And if you wait a very long time, the whole system is able to synchronize. Okay, so we mentioned defects. One of the interesting things that happens now is that you'll get these defects that also occur on, I got ahead of myself a little bit. So if we look at the synchronization in the array, there are a couple of things that are worth pointing out. One is that you saw that a lot of the beating, at least towards the center, away from the edges, remained planar. And so if you look at what's happening at the level of the individuals, so the black filaments here are what occurs at the center of the array, and the blue is what would occur for the isolated filament. The shapes are broadly the same, and what you see is that there's a, if you look at the curvature in a bit more detail, the curvature is a bit higher towards the base, so you get the same shape, but it's a bit bent over in one way or another, and I guess this is a result of the interactions with their neighbors. And you could also just look at how quickly the synchronization occurs by varying the forcing that you put on the end of your filaments to drive their motion. And you find that as you decrease your the magnitude of your follower force, the rate at which you synchronize decreases, so to take longer to eventually synchronize. Okay, so now what we'd like to see is what happens when we force this to occur instead on the surface of a sphere, where we know that these defects that we saw emerge have to remain because of the topology of the underlying surface. So here's a case where we have a fixed sphere we would describe as a lower force value, and at our lower value of a density of our spheres, or of our filaments on the surface. So here's what happens initially. You can get this coordination, and if you wait long enough, and long enough being about 600 periods of undulation, you see that you get azimuthal beating about a fixed pole. And what we can do now is say, well, what happens if we allow for our, if we increase our the magnitude of our follower force? So here's what happens kind of very early on in the simulation. And if you wait long enough, you get this, which is, you could characterize as a polar beating. So you get beating along the meridians. You could see a little bit that towards the pole, the pole moves around a little bit, just I think due to the kind of discrete nature of the filaments. And so what you could do is look at, well, what happens if we do a bit of a sweep and examine the net, I guess the average kind of angle with respect to, I guess, the phi direction, so moving, I guess, along the meridians. And you see that for the lower force values, you get this azimuthal beating, as we said. Higher force values, you get your polar beating, and you get this region in between where you have this transition between the two. This variation seems to be real. We're still running our simulations a bit longer, but there is kind of some variation of the average kind of beating angle with respect to the meridians in this kind of intermediate range. And one thing that we had noticed, and I'm just pointing this out because it's an observation we made, was that you get something similar in the planar cases, where For low values of your forcing, you get something that's aligned with the grid, but at higher values, you observe this beating along the diagonals, and this kind of connection is something that we're looking at more closely. Okay. So one thing that you could also look at is what happens when you start adding more filaments. So you go to higher densities. So this is this polar beating case that you saw. So this is the final state of what you've already seen. And you could see that if you're far enough away from where the defect forms, the beating is more or less planar. It's something very, very close to what we had seen with just the isolated filament, or what you would get in the array. And it's really just by the defect where you see that the motion of the individual filaments is altered. But when you go to higher densities, so here's what happens, you still get kind of polar type beating. But you can see even far away from the defect, you get kind of an out of plane beat where they're kind of, the filaments are bent over and performing their beating kind of not perpendicular to the surface. Okay, hold on. Okay, so if you, all right, so these are a bit messy, but I can explain. If you take your sphere now and unwrap it, so the poles are at the top and bottom here, and you now plot the motion of the tip of the filament over one period in the plane tangent, locally tangent to the sphere. So if you're just beating is planar, what you would just see are lines, and this is what we have in our lower density case away from the defects. But if you get kind of a blob or something that's not a line, as you see towards the pole, that that you're getting some altered filament motion. And so you see that when you go to our higher densities away from the poles, you get a lot of non-planar beating. And another way of quantifying this is to kind of take your these projections of the filament motion onto the local tangent plane and decomposing them such that you can draw this rectangle around the set of points that you obtain, and look at the ratio of the sides of this rectangle. For the lower density case, this rectangle is very thin towards the equator, but towards the defects is where you get your higher values, so more like a square. And but in the case of your higher density, you get this altered and kind of, I guess, three-dimensional filament motion throughout the surface of the sphere. Okay. All right, and so now I think one of the main things to think about is what happens when we let the sphere go. So we saw that you can have these defects that form on the surface. They can alter the motion of the filaments, cause them to bend over, do different things. That's when the sphere is held fixed. So how does this, imagine we let it go, how does this altered filament motion, how would that affect the underlying surface? So that's really kind of the question that we wanted to see or address. So this is a case where we now have a force-free and a torque-free condition on our body. And for the lower values of our force, what you find is that, or I should say lower densities, because it turns out that the magnitude of the force doesn't seem to matter so much. that you retain kind of an azimuthal beating, or you do get some motion of the pole about the surface. So it's really trying to stick around this kind of azimuthal type beating, but you don't see the polar one anymore, regardless of your value of the force. Okay, but remember, this is the case where many of the filaments were still executing their planar motion because we're at a lower density. Okay, and now I'd like to go to the case. So this is perhaps kind of the most interesting case, is what happens when we include a lot of filaments, so we can have a higher density. And I'll first show you what happens in the body frame, because it's quite interesting to compare the two. Immediately, what you see is that you get something that's very different than what you had in the fixed sphere case, and something that you might have, having looked at the bifurcation diagram earlier on, associated with a lower forced value, right? So you see that what you have is a bunch of whirling filaments. Eventually, what you see is that the sphere kind of divides into two hemispheres, one where you have clockwise whirlers on one hemisphere and anti or counterclockwise whirlers on the other hemisphere, and then something happening to the filaments on the equator that is in between. Okay, but what I think really kind of explains what's going on is not looking at what's happening in the body frame, but really tracking the lab frame. So you could see now, you could see these blue, I think they're blue arrows that are tied to the frame of the sphere. So you could see kind of what's happening with the rotation of the underlying surface. And what you see really, what's occurring is that the filaments are causing the underlying sphere to rotate, which is causing the filaments to whirl. So what you have really is a case of the tails wagging the dog and causing the bases of the filaments to actually move around in these little circles, and the whole system kind of feeds back on itself. Okay. And so one of the last things I'd like to point out is, so we said that we have these counter or anti-clockwise whirlers on one hemisphere, and then clockwise whirlers on another hemisphere. It's quite interesting to see what's going on along the equator, where we have a kind of modified planar type motion, which you could see in this, I guess, panel A here, we affectionately call a crab beat. So if you take your equator and unwrap it, you can see you get this kind of strip here. And then if you plot the tip height as a function of the azimuthal angle phi, or I guess the colors here show the tip height as a function of the azimuthal angle phi and as a function of time, you could see what's happening is you're getting a metachronal wave that propagates along the equator with a frequency, I think it's twice that of our whirlers. Okay, and another interesting thing about this is that if you were to look at the rotation now, so the angular velocity of the underlying sphere, this vector always lies in this equatorial plane and will rotate with this metachronal wave, right? So it's really this rotation of this angular velocity vector that's leading to the wobbling of the underlying surface. Okay. So I mean, that's more or less it. So just to kind of recap what we saw as far as the kind of synchronization goes. So if we had planar arrays, we just saw synchronization. You can get it either in the grid directions or along the diagonals, depending upon the value of this follower force magnitude. And what you see is that the motion of the filaments is something close to what occurs in the isolated case. If you put these now on a fixed sphere, you could either get polar or azimuthal beating, which may be something akin to what either grid beating or diagonal beating that you see in the polar cases. But what you can have happen now is that, or you need to have happen because you're on a sphere, is that you have the formation of defects, and these defects will alter your filament motion. And it's especially important at high densities where this alteration occurs kind of throughout the surface of the sphere. So then when you let the sphere go, if you have a lot of altered filament motion, that leads to an underlying rotation of the spherical surface, which feeds back and changes the coordinated state of your filaments. And I'll just kind of, one of the first questions I always get asked, so I'll just say it now. One of the things that kind of, I don't want to say burst our bubble, I guess maybe we should have expected it, was that there was no noticeable translation of our system, right? So we didn't see any net swimming of our body, which is why we couldn't call it a swimmer. But really what kind of motion we saw from the underlying surface is the rotation. Okay, so with that, I'll stop here, and I'm glad to take questions that you guys have.